Now we manage bodies. You specify the bodies that you want to use in your solution. And inside your managed bodies, you specify how these things are connected together. So you have multiple bodies. How are they connected together? If you have design constraints, loads, constraints. If you have scenery bodies, things that you don't want the optimizer to work, you specify your areas where you want the design optimization to work. Specify areas to keep in, keep out, etc. You would do in your managed bodies. So after you get your body all set up, you specify your material. If you have global loads, accelerations, type like that, then we set up and we run our optimization, and then we can go ahead and look at our results. Now, the important thing when you're doing this is to understand the design space. So the design space is the envelope that the optimizer uses. So when you are doing optimization, you want to remove areas to set it up as a big region for this design space to use. So in your original model, you don't want to make it all detailed. You want it as little, fidelity as you can. So you want the thing to be really nice and open so that you can take parts out and use all that design space. So with this, you get results. So you get new geometry, displacements, and stresses. So that's just a brief overview of the difference between these two topology optimizations. So I'm going to hop into NX and go over some of them. So here is a simple part in NX. So here we'll just look at it, and you'll see that there's some cutouts, things like that. It's been shelled. Now for our topology optimization, we don't want these regions shelled out. We want the optimizer to see this large design region. So we would make some changes in the CAD to go ahead and set that up. So that's what I went ahead and did in one of these other models that are open. So I just took that same model and I just gave myself this large design space. Now that I have this large design space, I can go ahead and set it up to be optimized. So the first thing that I'm going to do is I'm going to take this guy and I'm going to bring it into Sim Center or Advanced Sim. So to do that, we can hit Applications, Pre-Post. And now that we are in Sim Center or Pre-Post, let's go ahead and create our new Fem and Sim. So new Fem and Sim. I'm going to create the idealized part. In this case, I'm not going to use it, but in case I need to ever go back, I can change this idealized part. I won't mess with this part right here. So in this case, I'm going to set it as a static solution. It's a good idea to run a linear static solution to begin with, and most likely run a normal mode solution. Let you know where you're starting with, and then you can go from there. So now that I have my model brought in, set up, I have my Fem part, which I'm working on right now. Let's go ahead and mesh this. Now, since this was created in a CAD environment, I'm not too sure mesh mating conditions were created between these two faces. So let's go ahead and specify mesh mating conditions. If I would have cut this at the idealized part, I would have specified mesh mating conditions, but since it was done outside of SimCenter, let's go ahead and specify mesh mating conditions. So what this does is, now that these are separate bodies across this region, when I go ahead and mesh it, I'm going to have nodes that align with each other. So it helps me in my meshings. So let's go ahead and throw a mesh. So I'm going to put a mesh collector, and I'm going to give it a name. And then I'm going to go ahead and define the solid property. And in this case, I'm going to define a material. And I'm going to use my library materials that exist. If I had to type my own material, I could create my own material. But in this case, I'm just going to use 6061 aluminum. So now I have my property. Let's go ahead and throw a mesh on there and reference that property. So I'm just going to highlight the part. I'm going to use this little calculate element size, and then I usually go around half that, maybe sometimes a little bit less to get a nice mesh on the part. Now, if I wanted to change some of my mesh options, I could go ahead and do that here. You see it's going in the collector that I specified. Now, if it will automatically create a collector, so you don't need to create a collector. I like to create them ahead of time. It's just my order of operation, how I like to go about it. So now I'm going to go ahead and mesh the part. All right, as you can see, the part has been meshed. To help my visualization, let's go ahead and change some of these colors. I'm going to go ahead and find the center section. Yep, and let's go ahead and edit the display, and let's change this mesh to be blue. Just helps me visualize the difference. And in this case, I want to use the blue area as my design space. So let's see if we can remove some material and get good quality results here. All right, one other check that I like to do here is let's do a duplicate node check. Let's just run through this just in case. I know I did mesh mating conditions, but you never know. No duplicate nodes, so model's good. I recommend running some more checks in this case, but we don't have too much time, so I'm trying to get it all in. All right, so now I have my finite element model set up. Let's go ahead and go to the sim part. And at the sim part, let's go ahead and put some loads and constraints on this. So I'm going to go ahead and put a fixed translation constraint at the bottom. So I'm going to right click down here on constraint container, create a new constraint, fixed translation. You can always do it from the pull downs as well. I prefer the right click method. Yes.
Sorry to interrupt. Christine was wondering if you could change the color again.
Yeah, sure. So I'm going to apply these constraints real quick. So all you have to do is at the FEM level, if you go to the collector, you specify your mesh, and I'll just grab the other ones. And you just right click, and you can say edit display, and then right here is color. You can change the width as well, and you have some other options. So instead of green, give them red. And now if I hit OK, now those have became red. I apparently changed this one. Okay.
Thanks.
Yep. So it's just this display. When you write, my recommendation is right click on the level, and then right there, a lot of these have edit display, and then from there you can edit display of a lot of the entities in the tree. Okay. So I'll hop back up to my sim part. I have it constrained in this direction. So let's go ahead and apply a load to the structure. As you can see, I didn't change the color at this level. I changed it at the FEM part, so that's why it's different here. So now I'm going to go ahead and right click on loads, say new load, and I'm going to apply a force. And I'm going to apply a force to all these, I'll say pin locations at the top. Now I could create a group and make this easier, but I only have force selection, so it's not too bad. Now in this case, I want to apply a load in the negative X direction. So I'm going to symbolize somebody getting up and yanking on the seat in front of them to pull this thing back. So if you would think this would be right up below the handrest on like an airplane. So this would be the bracket that would, connect at the bottom, and this would divide the passengers. So we're just symbolizing somebody's pulling back on it, and I'm going to specify my vector in minus x sub c, and I'm going to enter in a value of 5 kilonewtons. So there I have my force of 5,000 newtons. I could have put e to the 3, apply. And now I'm going to apply it to the same location, but I'm going to symbolize somebody, I guess, getting up as well and pushing down on this entity. And this time my force is going to go in my negative z direction. And I'm going to specify a value of 11,000 newtons. Now, for instance, maybe you didn't know the value in newtons, or maybe you wanted to specify it in a different unit system. You could specify whatever you wanted here. So this is the one nice thing is with the units, maybe if I knew this value in pound force, so it's about 2,400 pound force. So I could enter it in like that. And those are, inconsistent units, but at least I have the same values as well. So that is not a problem inside SimCenter to do that, like in that type of solution. So now I have my entity set up. I have constraints, loads. I can go ahead and solve this model and look at our basic solution. So in my case, let's go ahead and solve it really quick. So it's sending the analysis in Astra, and this should take a couple minutes. So what we're going to do next is we're going to go ahead and set this up for optimization. So we're going to minimize weight of the structure. So a nice thing to check real quick is what is the weight of the structure. This is always a smart thing. So I could say checks, and let's go ahead and give it a solid property check. And I'm going to go ahead and check the solid properties of the structure. So I'm going to grab all these elements, hit OK, and it's going to list it in a table for me. So I can see right now my structure is about what 5.5 kilograms, give or take. So when we go ahead and optimize it, now we know where we're starting at. And I'm going to go ahead and write it down so I don't forget. So this solution should be all but complete. We're just running a static solution because maybe we want to use some of this information for our next solution. All right, so now I have results. I can go ahead and post-process them, look at what we have. Maybe we're interested in displacement in the X direction. So when somebody yanks back on that, is it going to, how far is the seat going to move? Is it going to hit it? Maybe there's some sort of regulation. So we can change our contour plot, hide some of these elements, make it easier to see what we have. Maybe we're interested in all this design space and we want to look at it, put annotations and see, oh, well, this location right here has a maximum of 0.35 millimeters. But maybe my regulation is, oh, this thing can actually move 3/4 of a millimeter before something happens. So maybe when I go ahead and optimize it, I'll say, hey, you can move, all the way out here, and that's fine. You still meet my design criteria. So that's one of the nice things that you can do with optimization. So we're not going to use any of the information here. I just think it's smart to look at our baseline, see what we have, and then let's go and optimize it. So now that we have this set up, let's go ahead and create a new solution. So you can go back to our tab and hit new solution. You can also right click down here, whatever you prefer. And this time we're going to go ahead and specify solution 200 topology optimization. And I'm going to accept the defaults now, and we'll get back to there in a second. Now in this solution, let's go ahead and grab those loads and constraints that we specified earlier. So now I have my loads and constraints defined. Now we have to go ahead and specify the other entities. So our design objective. So let's right click on our design objective. And what we want to do in our case is we want to minimize compliance. So we specify our design objective. Remember, we're only allowed one per solution here. Now let's specify our design area. Let me go ahead and unfringe plot that. There we go. So specify my design area. So I want to specify the optimization area. So I'll give it a name, optimization. Here's the optimization area, and I'll just give it a label as 1. And now the optimizer will know this as area that can be optimized. Now you do not have to do this, but I like to do it just in case, and it helps me understand what I'm doing as well, is you can specify the frozen area. So these are the areas where the optimizer is not going to use. To me, I like to define both, but maybe you have a large structure and it's easier to define one or the other. That might help. So for my case, it's pretty straightforward to define both. And it just helps me visualize that I specified the correct things as well. Next thing that we want to do is define a design constraint. So let's go ahead and right click on design constraint, new design constraint. And in this one, if you remember when we looked at our mass, it was a little over 5.5 kilograms. Maybe regulation or some sort of parameter saying, hey, let's get this thing down to around 2 kilograms if we can. And let's go max, we'll say 2.5. So we're trying to go a little less than half of the weight of the structure to begin with. So this is a decent amount of change to get there. So one thing that is important when you are doing these, you can't put some lower limit of like 0.0001. It has to be a reasonable value. So it's nice to give it a value which it could achieve. So now I have my constraint, and I'm going to define a manufacturing constraint. And this time I'm going to say planar symmetry. So I'm going to grab something on this plane. For me, I'm going to grab, I guess, a node right here, this curve. And I can just say midpoint. I'll grab the midpoint, and I'll specify the symmetry in this Y direction. which is this way. So it's symmetric about the center of the structure. So when I get results, it'll be symmetric about that structure. So understanding the manufacturing constraints is pretty powerful. Now, one other thing that we could do down here at our subcase level, maybe we wanted to add an advanced design constraint or another design constraint, and we want to say, oh, let's say the displacement of, I'm just going to pick a random node. This node can't be greater than, here's my lower limit, and it can't move more than 3/4 of a millimeter. So if I wanted to specify more design constraints, I could specify them. Or maybe I wanted to do an advanced design constraint. And inside here, I'd say, oh, well, instead of this, I want to say the stress of, the solid property. I'm going too fast, I'm sorry. So you could say the stress of some sort of property, and I want to limit that to be less than some sort of MPa. So if you add on more and more of these responses, it's going to take longer to solve, but you will get good quality results, and it will based on these responses that you specified. So now that I have my model set up, I'm going to go ahead and solve it. Now this takes a decent amount of time. So one thing that I would do is go to my solution, make sure it's the active one, and I would say, oh, I want to give it 60 cycles, and I want output at initial and all improved, so I get output at every time it went through it. Now, after you would set this up, if you need to change any other parameters, maybe you wanted to use a different optimizer, you could change that. So I went ahead and solved it on another screen just because it takes a decent amount of time. So now we'll just say I solved it, and now I have my optimization results. We can go ahead and look at it. So it'll give you, and I ran 50 design cycles, you can look at the static results, and you can also look at this thing called the normalized mass density. So it's a good way to visualize the load path. So I can see after my 15th design cycle, it thinks this is going to be the load path of the structure. And now I can go ahead and look at my last one. So I'm going to look at my material density results, but I'm going to look at for my 50th case. And it thinks this would be the optimization of the structure. And if I zoom in, you see it bored some holes out of there. But maybe I didn't want that to happen. I would have to enter in some more design constraints to make sure that this would be a solid part. So for my instance, I probably wouldn't want this, but I would have to try a different design constraint. You can look at from your results. So it's giving me what elements it thinks it should keep based on this model. So this is a great way to go ahead and start your design. You can look at this right from here. You can go ahead and export this out as an STL file, and you could map this on the original part, and then you could go into CAD and cut out these regions and re-bring it into FEA and solve it again and look at your results. The other thing that you can do is export this out as a verification solution, and what that does is it creates a new solution for you. And I already did this, and it just has all the elements in the model. So it creates a new solution that you can solve linear statics or modes or whatever you solved in the original and look at stresses and strains. So that's a nice little verification. What I recommend doing is getting your BDF file as you export out here as a BDF. So right here you can hit export and export out, and then just clean it up a little bit because you have some erroneous elements that might not be needed for that solution, and just get a nice quality model as you would think to go ahead and solve it. So that's the optimization in SimCenter. I know I went through it pretty fast, but I want to make sure I can spend at least 10 minutes or so on the designer optimization as well. So I'm going to go ahead and pop over here into my next one, which would be using the topology optimization in NX. So you can see I changed my design even more. So I have this whole region to use optimizer on. Now, in this one, it is a tab inside NX, not in SimCenter, and it's a topology optimization. It is a separate installation. So the first thing that I do is I'll assign materials. So select the entity. And this entity, just like I did before, is 6061 aluminum. And now I need to manage bodies. Now I only have one body, but imagine if you had multiple, bodies setting this up. You would have to then do a connection from one body to the other. In mine, I only have one body, so I'll grab the body. I'm going to add it to the list, and this thing is going to be design space. So I'm going to say, oh, we're going to use this material, and we're going to use this as design space. So inside here, we'll manage our design constraints. So in this one,